In the first part, I'm going to discuss about the basic theoretical aspects of binary search tree. What is search tree? What is the basic concept of binary search tree? How to insert an element in a binary search tree? How to delete an element from binary search tree? Then traversing BST. There are three kind of traversals: in-order, pre-order and post-order traversal that you are going to see today. And in the second part, I'm going to show you the hands-on C programming of inserting nodes and in-order traversal. So first of all, before going to the binary search tree, let us understand what is search tree. So a search tree is applied for locating specific keys from within a set. So this is the search tree. So search tree not necessarily always be a binary search tree. It can be other than binary search tree also. Okay. So what is the advantage of search tree? If the main advantage is that if the search tree is balanced, then it provides efficient time for searching. Okay. If it is balanced means number of nodes between left subtree and right subtree, if it is a binary search tree, are almost equal. That will be called balanced search tree. Okay. So in any kind of search tree, you can actually carry on these following operations, which are nothing but searching an element and then finding minimum, maximum, predecessor. Okay. And then inserting an element in a binary search in a search tree, and then deleting an element from a search tree. So these all operations are possible in any search tree, not necessarily only on binary search tree. Okay. Also, the other usability of search tree is that we can use search tree both as a dictionary and as a priority queue. Now, what is binary search tree? So binary search tree, you can look at, this is a binary search tree, the right side of this is a binary search tree. So what is the definition? The definition is that is a node based data structure. Binary search tree is a node based data structure where each node contains a key and two subtrees, the left and the right. So this is the left subtree and this one is the right subtree, you can call it. Okay. But then there are some additional constraints also. What are those constraints? For all nodes, the left subtree's key must be less than the node's key and the right subtree's key must be greater than the node's key. Okay. So these are something. Okay, these subtree must all qualify as a binary search. Now meaning is that this is my left subtree, this is my right subtree. So in the left subtree, all the elements should be less than 6 in this case, and the right subtree, all the elements should be greater than or equal to 6. Okay. Now when I am considering this node, this all elements should be less than. An immediate element definitely should be less than 6. And then if you consider 5, then this is the left subtree and this is the right subtree. Okay. So in this case, in left subtree, all elements should be less than 2. And the right subtree of the 5, all the elements should be greater than or equal to 5. This is the fundamental concept of binary search tree. Here also in the right side, all the element must be greater than or equal to this 6. Okay, that means 7 is greater than 6. And again for 7, there is no left subtree, but this right subtree is there, which is nothing but 8, which is greater than 7. So this is a binary search tree. This is the definition of binary search tree. You pick any node and then from this point of view, 6 right subtree values, all values should be greater than 6, left subtree all values should be less than or equal to 6. Okay. And then for this should be true for individual values also. For 5 should be greater than 2 and this side 5 should equal to or greater than this side of the 5, this side of the 5 should be equal to or greater than 5. That is a fundamental point of binary search. So this is also a binary search tree. This is a root node, and the right subtree, this is the right subtree. All the elements are greater than or equal to 2. In case of 5, this is the right subtree, no left subtree it has. So all the elements in this subtree are either greater than or equal to 5. In case of 7, this is the right subtree, which is 8 greater than 7. In this case, this is the left subtree of 7. 6 is less than 7, 5 also less than 6. So this is a proper binary search tree, both the cases. Okay. So if we insert an element, the situation is something like that. Let us say I have an element 7, 2, and then 5, 6. If I want to make a binary search tree, then how it will be? 7, 2 left side, then 5. 5 is less than 7, so it will come over here, but 5 is greater than 2, so 5 will be inserted over here. And then 6 is greater than 5, so it will be here. So this is also a binary search tree. Okay. Let us go to the next point. So in a simple sentence, we can say that for each node in a binary search tree, the left subtree is smaller than it, and the right subtree is greater than it. Okay. So in this case, if you see, first of all, whether this is a binary search tree, this is not a binary search tree, because this 24, which is of right side of 25, but 24 is less than 25. So right subtree, all the values should be greater than 25, but 24 is not greater than 25. So this is not a binary search tree because of this one. So instead of putting it over here, if you put it over here, then it is a binary search tree. But 24 is creating a problem, right? So for each node in BST, the left subtree is smaller. So this is left subtree, which should be smaller than it, and the right subtree is greater than it. So right subtree is this one. So this is binary search tree. Okay. Now it is binary search tree, but if you add 24 over here, then it is not, because 24 is less than 25, but unfortunately it has come to the right side of the 25. So this is not a binary search tree. If you delete it and then if you put it over here, then it is a binary search tree, because 24 is greater than 22 and 24 is less than 25. So it has come to the left side of the tree, subtree. So then it will be a binary search tree. Otherwise, if you put 24 over here, then it is not a binary search tree. We have different type of traversal which are possible to operate in a binary search tree. So these traversal are, first one is Inorder traversal, second one is Preorder traversal, and third one is Postorder. These three types of traversal we can have on binary search tree. Now we have a shortcut method to find this Inorder, Preorder and Postorder traversal. That shortcut method is actually for Inorder traversal, it is LDR, left display right. So this is nothing but root, this is left, this is right. For Preorder traversal, the shortcut technique is DLR, display left right. post order traversal, the shortcut technique is LRD, left right display. Okay, so let us see how it operates. First we'll check for in order traversal. So remember that in order traversal is we have to visit left first, left subtree. Then when we don't have any options of visiting left subtree, then you have to display the node, and then finally we have to visit the right subtree and display it. Okay, so these are the three ways we can do it. So always we have to start from the root node. Okay, so 25. Now I have to apply here LDR. So go LDR means go left, then display, then right. Okay, go left, then display, then go right. So 25. So whether we have any option of going left, yes, we have option of going left, which is nothing but 19. In 19 again we will check LDR. Okay, LDR. Whether you have option of going left, yes, we have still option of going left. We can go over here, we can come over here, and then 8. At 8 we don't have any option of going either left or right, so it is better to display 8. Okay, so display 8. Then once 8 has been displayed, come back over here. Then already left subtree has been exploited or visited. So next is 19. Whether any option of going left, no. So according to the LDR left subtree there is no option. So next display that node. 19 will be displayed, and then come back to right, which is nothing but 24. Whether any option of going left, no. Any option of going right, no. So 28 is the node which we should display. Okay, 24, sorry, not 28, 24. And this has been displayed, this has been, then come back over here 25. All the node of 25 which is of left subtree has been exploited or visited, so it is the time that we should display LDR. So all left subtree has been now display this 25. Similarly you come back over here. Shall we display 27? No, because we have option of going left, because shortcut says that LDR. So it will come back over here. 26, there is no option of going left or right, so display 26. Then come back over here, display 27, and then finally display 31. This is in order traversal. Okay, similarly we can also carry out pre-order traversal. Okay, so pre-order traversal is nothing but DLR, which is pre-order DLR. Okay, so first you have to display whichever node we will encounter, we have to display first, then we will visit left, and then we will visit right. So first we are starting from here 25. Shall we display 25? Yes, 25 we should display, because pre-order traversal say that pre displays at the prefix, so it has to be displayed. 25 displayed. Then 19 it will come. 19 will be displayed or not? Yes, 19 will be displayed because it is pre-order. 28, 8 will be displayed. Then 24 will be displayed. Then 27, 26, 31. This is called pre-order traversal. Okay. Next is we have this post-order traversal. One thing has to be noted down, that in case of in-order traversal, it is actually, in case of binary search tree, it is actually printing the element, in case of in-order, printing the element in ascending order. First 8, then 19, then 24, then 25, then 26, 27, 31. In case of in-order. So in-order means ascending order, remember that. Okay. Next is post order. Post order is LRD. That means first left subtree, then right subtree, then display. In all this traversal, this post order traversal is little bit tricky. We should not display the node once we encounter it. Okay, we should wait and see left and right. So in case of post order, it is LRD, left, right, and then display. So as usual, we will start from 25. Whether shall you display? No, because we have option of going left. So remember, the left you have to go, then right, then you have to display. We have option of going left. So come back to left. 19. Shall you display 19? No, we have option of going left. Shall you display 8? Because 8 is not having any option, so display 8. Then come back to 19. Shall you display 19? No, because we have option of going right. It is nothing but LRD. So we'll come back to 24. So 24 is no left, no right. So display 24. Then come back to 19 again. Left pointer and right pointer, left child and right child both has been exploited or visited. So display 19. Then come back to 25 in case of post order. Shall you display 25? No, because you have option of going right, because it is left, right, display. Come back to 27. Shall you display 27? No, because you have option of going left. Come back to 26. No options are there, going right or left, so display 26. Next, come back to 27. Shall you display 27? No, because you have option of going right, which is nothing but 31. 31 is having no left, no right child, so it can display it. Go back to 27 again. Both left and right child has been visited. Subtree has been visited, left subtree and right subtree. Better we publish 27. And then finally go back to 25. Shall we display 25? Yes, because all is left subtree and right subtree has been visited, so 25. In case of post order traversal, you can see that the last node is actually the root node. So this is one observation. Okay, last node is the root node. So by that you can actually understand that it is a post order traversal. Okay, or you can catch hold of the tree. If the traversal is given, you can catch hold of the tree's root node. Okay, so this is how Inorder, Preorder and Postorder traversal works. Now we are going to see another important operations, which is nothing but deletion of a node. Okay, so deletion of a node, how to do? So deletion of a node from a BST having three cases: case 1, case 2 and case 3. Okay, so first is case 1. Case 1 is very simple. Let us say this is my node and I am going to delete this one. If it is a leaf node, then simply delete it, cut this connection and delete it. Okay, so in case of case 1, the resulting node will be 25, 27, 26 and then 19, 24 and then this is 8. So if it is a leaf node, simply delete the node and display the resulting node. Okay, this is case 1. What is case 2? Let us say my resulting node is this. Now I am going to operate. That means I am going to delete this 27 from this. Let us say this is figure 1. This is my figure 2. From figure 2, now next I am going to delete this 27. So that means internal node with a single child, case 2. So if 27 has to be deleted, then simply you can delete it and you can pull back this 26 in its position. So the resulting tree will be like this. 25, this will be 26, 19, then 8, then 24. 27 has been deleted. That means internal node with a single child. This is there. This is case 2 also very easy. Now what is case 3? Let us see case 3. So case 3, case 1 is done, case 2 is done, case 3. Okay. Now in case 3 what is happening? Let us say this is my A, B, C, D, E, F, G. So let us say B has to be deleted. Okay, so B is having 2 children and then further E is having further children. That means B is having grandchildren, okay, like F and G. So if you delete B, then what? Then how it will be adjusted? So in this case, we have to see the in order successor. In order successor of that node. So in order successor means we can just simply run in order traversal over here. So LDR, go left, display D, then B, then come back over here, display F, and then E, and then G. So after B, in order successor is F. Okay, it is F only. So F will occupy this B's position. If you delete B, F will occupy this position. So that is called in order successor. This one. Okay. So the resulting tree will be like this, something like this: A, F, E, G, D, and then C. Okay. So this is case 3. So all the 3 cases we have discussed how to delete a node from a binary search tree. Okay. So next let us going to see the recursive function. Previously we have done with the shortcut method. The shortcut method is handy when you are solving problem, but normally in most of the cases this BST traversal algorithm runs in a recursive fashion. So this is the function we have, and also in the later phase of this lecture, that C program I have implemented for insertion and in-order traversal, I have exactly used this function, recursive function. So this is a recursive function. What is recursive function? When function calls itself. So in-order traversal is calling in-order traversal, right? This is calling in-order traversal. This is like a recursive function. When function calls itself, it's called recursive function, right? Now let us see how this recursive function can be applied to calculate the in-order traversal. Okay. Earlier you have done with the shortcut method. Now let us see in-order traversal how it works. So for that, what we will do, first we will. So here remember that node original is nothing but the root node. Okay. So node original then we have left pointer to left child, pointer to left child, and then finally we have pointer to right child. Okay, these are three. First is node original, that means root node, pointer to left child and then pointer to right child. Okay, let's see how it happens. So this algorithm says that if node original is null, it returns the value. Okay, it returns, and then next it calls node original recursively. Okay, it calls node original pointer to the left child, and then it is printing the key value in the node, and then further it calls again node original pointer to the right child. So this recursive, we have this recursive calls 1, 2, these recursive calls are there, and in between you have to display it. Okay, so first we'll start with 25. As always, as usual, root node has to be passed over here in node original, which is nothing but root node. So first is 25, then point at 25, right? So whether 25 is null? No, 25 is not null. And then it will come over here, Inorder traversal, node original, pointer to the left child. So pointer to the left child is this, pointer to the left child. Okay, 19. So you should write over here 19. Whether 19 is null? No, 19 is not null. Okay, so it will again come here, come over here. So it's a recursive call, remember that. So Inorder traversal, node original, pointer to the left child. So what is the left child of 19? Which is nothing but 8. It has come, the control has come to 8. Okay, so then whether 8 is null? No, it is not null. But Inorder traversal of pointer to the left child, node original, if you call, pointer to the left child is actually null, right? If it is so, then display the key. Display the key, that means display 8. Okay, display 8. Then Inorder traversal, node original, pointer to the right child, done. So next is, so after 19 you have 8. So 8 left pointer and right pointer both has been visited. Okay, and then finally we have this, after 8 we have null. So null left and right. So null left and right we have visited, right? Next, control will come to 19. Okay, control will come to 19. Now 19 left child has been visited. Yes, 19 left child has been visited. Whether 19 right child, 19 left child has been visited. 8 left child and right child both has been visited. Okay, null left child, null and right child doesn't matter. So next is 19. So 19 left child has been visited. What about the 19 right child? 19 right child has not been visited. So 19 right child has not visited. So here it is like 19 node original, pointer to the left has been visited. So 19 will be displayed. Key of 19 will be displayed. Okay, then it will come here 19. This call will be there, recursive call 19, pointer to the right child of 19. Pointer to the right child of 19 is 24. Okay, so 24, whether 24 is null, but 24 left pointer is null actually. 24 left pointer is null. So in that case, key 24 will be printed. So 24 left and right both the pointer has been visited. So it will come up over here, right? And then it will go to 25. 25 left. 25 is null. No. Node original left pointer has been visited. Yes, left pointer has been visited. So it will return. So you have to print the key. 25 has to be printed. So similarly, like 20, so 19 left child, right child. So 25 left child has been visited left pointer, and then it will be displayed. 25 will be displayed, and then right child will come over here. Okay, after displaying 25, So 25 right child is 27. 27 left pointer is there, yes. 27 left pointer, left child is there. 26 left and right pointer, nothing is there. So 26 will be displayed, and finally like this fashion 27, 31 all will be displayed, right? So this is the in-order traversal using this recursive function in-order trav. Okay, so if you minutely see this is nothing but ascending order traversal. Okay, so in-order traversal actually gives us ascending order traversal, right? So now we are going to see the C programming implementation of binary search tree. Okay, so as usual, because this program deals with pointers, pointer to the left child and pointer to the right child, which is of structure BST type. Okay, so it needs a structure, data structure. Okay, it needs a structure, so abstract data type. So this structure BST has three fields. First is key, second is pointer to the left child, third is pointer to the right child. Okay, and then we have a function to make a tree. Okay, and then we'll be using this pointer node which will accommodate this malloc function. Okay, malloc function doing typecasting and all. Initially this left pointer and right pointer both will be null initial cases. Okay, and then we are having this insertion of node where we will pass this root node and key, initial key. Okay, so here so once we do that insertion of node, this function will be called from the main function, where we are first inserting 25 as per our input, 25, then 19, then 27, then 8, then 24, then 26, and finally 31. And then we are having in-order traversal call. And then already I have discussed this in-order traversal, how it is happening. Just couple of minutes back I have discussed. This is how this in-order traversal is happening. Okay, so this is the full C implementation. Just have a look. Let us run it now. So this is the tree we have. So if you see our insertion, so our insertion is like that. So we have started with 19, we have started with 25, then 19, then 27, okay, then 8, and 24, then 26, then 31. Now if we run a in-order traversal over here, then which other nodes will be displayed? First 8 will be displayed. You can see that first 8, then 19, then 24, then 25, 26, 27, 31. Okay, so 8, 19, 24, 25, 26, 27, 31. Okay, now one interesting thing with binary search tree is that the searching time is proportional to the height of the tree. Okay, searching time is proportional to the height of the tree. Okay, and this is, so in this program I have just shown you how to insert in a very simple way and how to traverse in terms of in-order traversal. Okay, so we can also write C programming for post-order and pre-order. Okay, you can try that. So I hope this lecture will help you to understand the basic concept of binary search tree, and also you have understood the programming concept, how to insert nodes and how to have a in-order traversal. Thanks for watching.